All right, so how are you guys doing today? You fine? Okay, perfect, great. So here's something I want to tell you today. I'm still working on the syllabus, but there's certain things I made a decision on. So I just want to let you know ahead of time. So most importantly, we're gonna do. Let's do this first. So you guys use this one, right? This one for your online homework, right? So I was contacting the people in the Cengage company, and I think they're able to transfer Dr. Gomer's class onto my account. So you can keep your Cengage account for your later homework, but you don't have to do the homework that was due yesterday. I got lots of email yesterday. I don't know, but you don't have to do that. I actually don't even know what the homework is about. I'll try to make a new one maybe sometime later, so you can do that. But you don't have to worry about the homework on Cengage at the moment from Dr. Gomez. Okay, so we'll keep this one here. There's one more thing I want to mention. There will be some additional online homework that I'm going to give you during the semester. I think about twice this semester. But you're going to do this as an extra credit chance. So that means it's not required, but it certainly will help you for getting more points. So you can maybe use it for the total grade calculation. That will be, I think, very helpful. So make sure, along with this one, beside this same is online assignments. We think we can keep this. I'll make sure that we'll do it maybe later this week. But make sure, additionally, we're gonna have some other online homework as your extra credit chance opportunity. Okay. All right. So that's it. Also, I want to mention about the exam. Okay. So this exam, we'll have a. Did you guys watch the first one, the lecture? Okay. So we're gonna have two midterm exams, and we're doing in person. So that means you're in group B, means Wednesday. In this course, we only have a group A and B, that is Monday and Wednesday. Okay, and then I'll just try to choose the week. So I think it would be your first midterm exam will be around at the beginning of the October. So we still have about like a month to get to the first midterm exam. And then that week, the first or beginning week of the year, October, you only need to come on Wednesday. Okay, so there will be on Monday. There will be other Monday part group student will come and do the exam, and you only need to come on Wednesday. So that week of the exam week of the semester, you're not going to see any lecture video posting because the other days other students are taking the exam. There's no lecture, but you only need to come once per week, which is your hot days. It makes sense, right? So there will be first one will be at the beginning of the October. So we have another one. We have the other one here for midterm. There will be, I think, it will be the mid-November, right before Thanksgiving. Okay? Right before Thanksgiving. So that would be the second midterm exam. I don't know if you already got this from the first lecture video. You can actually drop the one lower midterm grade. That drop the midterm grade will be replaced by percent score of your final exam. Okay, so that will make you a lot of room to do really well in class in the very last minute of this semester. So do not give up. You still have a lot of chances during this semester, extra credit, and this exam policy will make you do well in class very last minute of this semester as well. Did you already got this from the first lecture video? Okay, so this is something what you can do. This morning, one student asked me if they can work kind of somewhat against you, like you did really well on these two midterm, 100, but you did maybe 80 on the final exam. where this will replace one of your midterm grade because this is lower. So maybe you can maybe replace by 80. Maybe you can do like this. No. So I'm only going to replace one of your lower midterm exam by the percent score, the final exam, when it's make you better total grade. If it's not, I'm not going to do it. You can keep the still there's 2 good grade on the midterms. Even the final exam score is percent score of the final exam is lower than those. Makes sense, right? So it's always better. So this is really good exam policy we're gonna do this semester. So you have a lot of chances to do well in class. Okay, sounds good, right? Do you have any question other than this? Okay. All right, sounds good. So this is something I want you to keep in your mind for this semester. But I'll finalize the syllabus whenever I have another contact from same-based companies. I'm almost done with making all the syllabus. But I'll try to finalize the syllabus by hopefully later this week. Okay. Yeah. Oh, I haven't finalized them yet, so that's a good question. So basically, each midterm, I didn't finalize it, but my plan right now is each midterm takes worth of 100 points. So there'll be 2. So that means in these 2 midterms, you have 200 points you can earn. And the final exam, usually they're double size of the what you're normally seeing in the midterm. So final exam, my planning is 200 points. And your another 100 points will come from your assignments. So that is from your Cengage or the some other homeworks we may do in the semester, but mainly from Cengage. And you can have some extra credit from the other additional online assignments. So for now, your total, the points in this semester for your grade is 100 points, 500 points. So if you're getting like 450, it's guaranteed A. Okay. But this is a kind of a sort of a plan. Yeah. But I'll finalize this sometime soon. So it's a really indeed, if you look at this, if you do well in the final exam, can change almost everything. That is the solely that doing well in the final exam takes like 300 points out of total 500 points. And if you do only one of the midterm exam well, it's almost guaranteed A anyway. But still, just gives a lot of room for us to. Okay. Do you have another questions? We're good. Okay. So, whenever I post the syllabus on campus, I'll also send you some notice, like announcements, so you can take a look right away. And also make sure, I've been telling this from the first lecture, make sure when you see the post the lecture video, every like Monday, Wednesday, and Friday, make sure you download it right away. Okay? Because we have a limitation of the campus capacity, so you can just download it. You don't. I'm gonna erase the first one and we're gonna put the next one later. Okay. All right. So today, what I'm gonna do, as I did this morning, I'm gonna try to finish the review on chapter 2, so we can move on to chapter 3 on Friday. But Friday in this course, I'll post the lecture video, so you can wait for the lecture video posting on Friday. So here's the thing: where we left from the first lecture was STEM based. Okay, so we talked about some 2 different definitions. Okay, like in the Bronsted-Lowry definition, and also the one we taught in organic chemistry is Lewis STEM based. So it's all about how we're gonna deal with this movement of the protons or the pair of electrons, and so forth. So in this case, there's something I wanted to review the chapter 2 because of this one. You'll see this number quite often this semester in organic chemistry. That is number for pKa. So pKa simply is number from negative log. So P value over here is simply negative log of something. Like if you look at the pH value, it's negative log of concentration of protons. That means this is a pKa, it's negative log of Ka. So if you recall, the Ka is simply what? Your rate constant. It will tell you the relationship between your molar concentration of reactants and your weight of the chemical reactions. So that means if you have a higher number for Ka, that is going to be what? Relatively speaking, faster chemical reaction you might expect in this number. But like I said here, pKa is negative log of something. So whenever you see the lower pKa, it actually tells you the higher Ka means what? You're going to have more numbers of proton as a product. That means we'll be indicating stronger acid. Okay, so this will tell you, this is number you can miss on in chemistry. So this is why I also wanted to review this point for acid and base. Okay, so make sure you guys keep this in your mind. So I can try to show you some examples here. Do you have any questions so far? We good, right? Okay. So please keep this in your mind. Okay, pKa negative log of Ka. So lower is a stronger acid. Okay, so whenever you can think about some of the whenever you think about, here's the thing. Do you know why we use Ka in the first place? Why we need the number for Ka? So we need a Ka for those ones. Do you know HCl, right? Hydrochloric acid here. So this is a strong or weak? Could you tell me? Strong, perfect. So that means whenever you do this in the water, there will be what? All fully dissociated like this. If you recall example 2, it's a heinous definition. Whenever you do, you remember this one, right? This is a hydrogen cation. So this is basically the same thing. Just the water is involved with another definition of the Lewis-Thomson acid definition. Anyway, so what it does is they dissociate in water. This is obviously because of hydration. And this is strong, as we know. That means if you write this one more precisely, that actually looks like this. Okay? It just, we don't see this one reverse because this is true strong acid. So it will be more on this side, dominant direction, forward direction, over the very, very weak reverse reaction. Kind of makes sense, right? So it's always both way, but we only need to know which one is more dominant. Okay? But this is an easier case now because it's very strong acid. We don't see this one very often. We can just simply say this is what happened in water. No problem, right? It's almost 100%. This is strong. How about this one? If you have a weak acid, it's not strong. Then maybe you can do this one. So it is still what? H plus F minus 49. Okay. I'll just do this one for you. Oh, with water. Okay. Let me do this one. Hydrogen cation plus fried anion. Okay, it's the same thing. But now this is weak acid here. So what you need to do, you need to consider this one. You cannot ignore this one anymore. And now this is where we need to consider what degree of this one were happening at the same time and both ways. And this is why we need the number for Ka or pKa. Makes sense, right? Whenever it's weak, it's not dominant one side. We need to know what's the one is going all four, reverse, which one that will be the equilibrium, and so forth. So anyway, whenever you do this, before I move on to the pKa, there's one thing I want you to remember this. Whenever we see this as a strong acid means is because it has weaker interaction between these two, weaker bonding. So that makes this one strong acid. Okay, that means you have a weak acid, right? Hydrofluoric acid here, and they actually have stronger bonding between these two. That makes this weaker acid. So it's all actually always the other way. Bonding and acidity of the compound is always the other way. So I'm telling you this because it's always confusing. It kind of makes you feel like if you have a stronger bond between these two, you feel like you're going to have a strong acid, right? It's strong, strong. No, it's actually the other way. So you need to keep this in your mind for this semester, so we're not confused you. Like, oh, you talk about the strong bond, but why is it not so strong acid or strong base? Because of this. So the way we define the acid or base is their dissociation rate. How can they apart easily? But the bond is totally the other constant, opposite constant. So strong acid will make very weak bond between two, and this one has a strong bond. That's why it makes this one weak acid here. So relatively speaking, this will be weaker acid. There'll be a lot less dissociation for the protons over here. Here's the thing. Can you guys guess why this is stronger bond? If you look at the periodic table. Yeah, right? This is electronegative, then this one, ACl, the fluorine here, and also size. So whenever I have a smaller atomic size, the bond between these two will be smaller, right? So you think about the columns below everything, smaller distance will ensure they have a stronger interaction. So that's why this becomes, relatively speaking, weaker than this one. It makes sense, right? So anyway, it makes sense, right? So anyway, so now we know why we need a period. And I'm going to show you how we're going to use it relatively speaking. Okay? So I'll give you one example. So now we know why we need to use K. Here's a how. So one example I can give you in the textbook is this one. Okay, it's acetylene here, and this will interact with the hydroxide anion. So obviously, you see there's one with the hydrogen, the potential protons, and this is the HO minus hydroxide anion. So this is obviously, this one is what? Acid. This is base. Okay? Obviously, right? Because this will try to accept a proton. Okay, or you can donate the electron either way. Okay. Anyway, so. Anyway, so we'll do acid and base over here. Then this is something I also want you to remember from second 2. You remember conjugate base, conjugate acid, right? Okay. So whenever you do this, you can do conjugate base over here. Okay, and plus water. Okay. So now we have this one ready. We have someone that donates the proton, they accept the electron. I'm sorry, the protons. That makes this one. So if this is an acid here, please tell me what this will be: conjugate, acid, or base. It's coming from acid. Now in the other side, this will be conjugate, base. Perfect. This will be conjugate base. Okay, perfect. So try to recall what you have learned in Zen-Chem 2. Okay, and this one obviously, once it's base, now it instead of the proton becomes acidic form. So we conjugate acid. Okay. So it all makes sense now. We know this has to be in a somewhat both way, but we still need to find which one is dominant by using pKa or Ka. And now this is how we set it up. It all makes sense. Someone accept the proton, the one don't need the proton. The other side is the other one from the other side. So the number that I'll give you an example is this one. Whenever you get this one, pKa for acetylene here will be 25. And the pKa for water is 15.74. So here's the thing. If you try to look at what we just talked 10 minutes ago, which one is lower? This is lower, right? So that means which one is the stronger acid here? Is it conjugate acid or just acid? Conjugate. So in this case, think about it. When you think about the K, like I said before, it somewhat determines the speed of reactions. So if these two happening at the same time, but this is much lower in pKa, which means the strong acid, which will be more willing to donate the proton than this one, interacting with the stronger base, which is conjugate base over here. So if you write it this way more precisely, it looks like this. So the reverse reaction will be more dominant. It's just because of your lower number in pK on the other side. So this is how you can use the number of pK for each acid or conjugate acid or conjugate base or base. So you can say, oh, this way has to be more dominant on the other way of reactions. Okay? So obviously, I think this is very important in chapter 2, and this tells a lot of information about also another parts of the later this semester. So this will be for sure on exam. This will be something I cannot miss. I cannot miss in chapter 2. So make sure you guys do this. Just look at the number for pKa. Make sure you do which one is conjugate acid, conjugate base from these two, and tell, oh, this number is lower, gotta be in this way, it's much more dominant. Okay? Or we can say more significantly. Okay? This is something you don't have to know, but if you don't know about the pKa value, just I don't know. Just you see that you have to just take a shot here. I would still choose this one anyway, not looking at the number for pKa. Can you guys guess why? I mean, I don't know. pKa will precisely, even very accurately judge which one will be dominant. Without looking at this number, I might say this one will be more dominant anyway. Can you guys guess why? This will not be on the exam. You don't have to know. It's just for your understanding. If you look at this one over here, this looks with the triple bond right here, the hydrogen. So I can say it's pretty, like you could do the hydrogen or in the orbital wise, you'll do the aerial next time, ARIO, but we'll do later. But anyway, this is pretty stable for me. Even water is quite stable too. Somewhat stable. And the game changer is actually from these two. Hydrogen anion is quite unstable as well, because this is negative charge here too. But if you look at this one right here, this carbon is a hydrogen, but this carbon only has a lone pair also with a negative charge. Now you're looking at the 5 electron on this carbon right now, which is quite something carbon don't want to have. So what they want to do is this is a bit more unstable than this one. Even though this is quite unstable, can compare with this one. This is very unstable. So, I mean, relatively speaking, I'm sorry. So this one actually wants to go in this way to be much more stable in some, in these two. Not just for these two, it has to be combination anyway. But you have to guess. Still, this will be the best guess. This is something you just need to know for your understanding. Sure, it will not be on the exam. Just wanted to tell you in chemistry, if you recall from Jenkin 1 and 2, everything, molecule, the atom, or the chemical reaction, they always tend to, most of the time at least, tend to lead to the lowest possible energy state. So they can be stabilized. This is something you can think during this semester, or almost everything anyway. Okay, so this is something we cannot miss. Right? But it makes sense, right? Do you see? Okay. So if you have any questions, just let me know. But this is actually quite straightforward anyway, especially to the pKa value. So we cannot miss this one, which is quite easy problems we can deal with it next time. Just one more thing I want to mention. For your calculation, you know the pKa and the Ka, right? So I said if you want to do the pKa, just you need to put the negative log of Ka, will make this one, right? Okay. Whenever you see this to the other way, what you need to do is put 10 and power this 10 by negative pK, and that's the Ka. Okay. So, for example, if your pK value was 10, okay, and the Ka value for that compound will be 10 to negative 10. That's it. Okay. So this is something you can do in your homework or any other, not even just this one. You can do it in any other type of chemistry. This is similar to the pH level too, right? Concentration of hydrogen, cation. Anyway, all right. So this is for your information. All right. So here's the thing. I think we're pretty much done with the STEM basic chapter 2. We have to do a little more in detail later in chapter, but good for chapter 2. The other thing I want to still briefly mention, one of them is a resonance structure in chapter 2, which is also very important. So whenever we think about the resonance structure, it gives the possible structure that can be made from the one compound. So whenever you're looking at this one, like you read the textbook, it says either you have like electrons available in the space, like a lone pair, okay? Or the electrons and the pi bonds. That simply means what? It should be in the either a double bond or triple bond, right? It's the double bond and triple bond is the combination of sigma bond and pi bond. So if they can do, maybe they can do some motion of the electrons here, and then make some different possible resonance structure for a same compound. This is the main thing. There's other rules you need to know. Actually, go ahead and read them. But this is quite something you can do, except the very few exceptions. So I'll give you one example here. So one probably you can find in the textbook is the carbonate. So you can look at the carbonate anion over here. You always are going to choose your first chemical element in your formula is going to be a central atom. So I'm going to put this carbon as central atom in the center. And I'm going to put the oxygen as surrounding atom, 33, so we put 3 over here. And then it has in total -2 net charge. So that means I need to assign the 2 additional electrons somewhere on some of the atom in the structure for one possible resonance structure. So I'll choose these 2, okay? I chose oxygen over carbon DY for assigned electron. I chose the oxygen over carbon. It's because oxygen is more electronegative. So it's always, so here's the thing. If you look at the resonance structure in a certain compounds, sometimes carbon carries a negative charge over the oxygen sometimes. But it's just simply because of the chance. Okay, I'm not going to go in very detail, but here's something I want you to know. Electrons, all the location of electrons in the molecule, in modern chemistry, we only do it by chance. So maybe we can say there's a 3 lone pair, okay, that makes these 2 negatively charged because you have a 1, 2, 3, 4, 5, 6, 7, but oxygen is group 6 element. So that has 1 extra electron than it should have. So it'll be negative charge. Same. So it'll be 3 lone pair, negative charge. And 2 lone pair. You suffer this one, 1, 2, 3, 4, 5, 6. This is pure charge. Carbon 1, 2, 3, 4, pure charge here too. So maybe you can say, oh, I'm confident. There should be 7 electrons here, 7, 4, and 4. Am I right? No. This is only for our easier calculation. This is not real. As you saw in the textbook, right? This is not real because did you see my first lecture video? The orbiter is not a real thing. It's just the mathematically calculated, hypothesized the 3D space where we can find the electron for high chance. So that means we're only going to see where the electrons are by chance. But as you know, by chance cannot be just something you can always rely on in reality. It's just something just you can estimate, but it's not a confirmed number. Okay. So anyway, whenever you look at this one, this is one possible scenario. So I'm going to assign the electrons on here. But at the moment, sometimes you see whenever electrons move on here over the oxygen, it's going to be like a negative charge in S or something. You see that sometimes in textbook because it's made possible in certain special conditions or very certain short periods of time. But this is something you don't have to know for sure. But anyway, just for your understanding. So anyway, so we already did this, assign the electrons in these two here. But as you know, the Lagrange structure, you can move this 2 lone pair on here to make double bonds, right? And this will make an electron like a potential push onto center carbon to this one. So they can go up to here. So whenever you do this, if you want to do the motion of a pair of electron, make sure you do double arrow. Okay? If you're doing only one, it's sufficient with arrow. Anyway, so that makes this one 3 lone pair under here. We're moving this one because this pair of electron become a lone pair here on the top. By push, this become a double one here. We're moving one electron here. So that makes here to what? Oh, sorry. Was it? Yeah. This one, this one, right? Okay. And you can do one more, right? You can do either this one, and this one over here. Okay. So this is a 3 possible. This is a 3 possible resonance structure you can get from the carbonate anion. But once again, in reality, what you're gonna see for this one is the resonance hybrid. So what you can say is I already showed you if you took second 2 from me, but what it actually happened in reality is negative 2/3. So now you can say, what do you mean negative 2/3? Electron can be split now. We're using the chance again. This is by chance. So the chance you can find the electron near here is about 2/3. That's what it means. 1 electron. Okay. But overall, if you do the sum, the net charge is still negative 2. And this is what the nature does, is indeed by like a probability map, not the actual location where we see for sure there. No. Okay. So this is more precise. This is a bit different from our, organic chemistry from organic chemistry. We'll do it more in a more realistic way. Okay, makes sense, right? You good? So this sounds great. So make sure you guys just do a bit of a review on chapter 2 again before we move on to chapter 3. I know you already gone to some midway into chapter 3. We'll get there soon, so we can. But this is really important, so I'm going to just re-emphasize once more. Okay, so we have 1/7. Okay, we'll make it a bit shorter today. So there's one more thing I want to mention before I wrap up with chapter 2. Before we move on to chapter 3 is the intermolecular force. This is something also I cannot miss, as you can already tell from first and second lab in this semester, vacuum range, right? We have recrystallization, solubility. What's the solubility? What's the solvation? What's the solvent? What's the solid? It's all from the guy, intermolecular force. So obviously, when we talk about the organic compounds, something we cannot miss is London dispersion force, right? London dispersion force. This is so by the way, intermolecular force is literally what it says. It's all interaction among the molecules. So there's no intermolecular force from one compound. No. It's only possible when you have multiple numbers of molecules. So this is interaction among non-polar molecules, plural, right? And then this stronger interaction is dipole-dipole interactions, as you learned before, chapter 2 and in previous course. Okay, dipole-dipole interaction. And also, most importantly, I want you to remember this hydrogen bond once more. This is quite important too. So whenever you get this one, dipole, obviously, this is the reason why we went over the dipole moment once more in organic chemistry. Which chapter 1 or chapter 2? Dipole moments. We cover in either chapter 1 or 2. So there's a dipole moment we learned in Chem 2. And also in either chapter 1 or 2, you have a dipole moment once more because of this one. The dipole-dipole interaction simply means what? The dipole moment and the molecule, they have a slightly positive charge, slightly negative charge. Because of this, the change in electric potential on each side of the molecule, they will also experience slight, relatively speaking, quite a somewhat strong, somewhat weak interaction among these two. Okay, so this is dipole-dipole interaction. But if they are in, for example, most of the good non-polar molecule will be the ones the same elements are made of covalent bond on each side, because there's no zero change in the electronegativity that makes this compound in total non-polar. So there will be no change in both ends. So this, relatively speaking, this will make interaction. This will be a lot weaker than this one. There'll still be some interaction between these two because of what we just talked about the legend structure. What is covalent bond, by the way? Covalent bond is what? The co is perfect, sharing the covalent electron. So they sharing valence electron, the way it can use for the bonding in the most outer shell, but they're shared together as covalent bond. And this is where you can see it. Okay, perfect. That's a good answer. But if you look at this one, if there's no change in the electronegativity, the same chemical elements, by chance, the bound electron here and here will be the same, right? But think about it. Like I said, in reality, it's not always true. The chance is 50-50, but whenever you do the dice rolling, it's not always 1/6, right? For the one number. Sometimes this will be 51%, 49%. Well, you never know, but it's slightly different sometimes, and only certain short period of time. So this molecule can be instantly slightly polar. Not always. So for the whole time it will be non-polar. But there's a little bit of ups and downs because of the motion of the electrons that makes slightly polar at very instant time. That still gives this non-polar molecule exceptionally slightly polar at very short period of time. And that during that time period, they can still do the interactions. So there will be no interaction, no. There's still some interaction, but very, very weak. This is what we call London numbers. Dipole-dipole, obviously polar-polar. There's change in the electron among the molecules. There's definitely interaction by following the Coulomb's law. And the hydrogen bond is a bit special because this is the strongest dipole-dipole interaction. So we kind of separate it from the regular dipole-dipole interaction. We call this hydrogen bond. It only possible when the hydrogen is interacting with either nitrogen, fluorine, and oxygen. And also, this also has to be covalent bond to either nitrogen or fluorine or oxygen. So a good example of this one would be water. Okay. I'm sorry. So anyway, this is something I want you to remember before you go into chapter 3. So do you have any questions? It looks very straightforward. This is what we already learned in the previous semester. So, but I think that will be a good review for this beginning of the organic chemistry semester. Okay. All right. Thank you, guys. That's it for today. I'll see you next Wednesday.